All right, let's do an example where we're just working with an object that's rotating. So in this case, we have a helicopter blade. So make a quick little, I'm just going to make something that looks like this. So we have helicopter blades. They give us a length of each blade, and we know that is rotating. So I'm going to put just a little so we know they're rotating. And they're rotating at 550 revolutions per minute. And we know that each one, I'm just going to call this the length. And we want to know the linear speed of the blade tip. So that's the first thing we want to look at. So if I want to know the linear speed of the tip, so that's going to be the point. So the whole blade is rotating, right? But let me make a little kind of circle here. So the whole blade is rotating, but we're interested in the speed of the tip. So I'm going to just draw in my little velocity vector pieces here. So we're interested in the speed of those, or the magnitude essentially of these little arrows that I put in here. So that's my velocity vector here. So we want to know this, the speed of the blade tip. And so we're going to introduce a couple of quantities that we're going to use in this section or anytime we're working with circular motion. So for A, we want to remember that speed is just a distance over a time, right? And so if I think about something moving in a circle, we can represent the distance that it covers. So as it goes, so we're going to say it does one complete cycle. So if I start here, go all the way around and come back, the distance that it's going to cover is going to be equal to the circumference of the circular path it is taken. So our distance is going to be equal to 2 pi r. And the time it takes to do that, the time it takes to do one complete revolution has a special name, and this is a period. So we're going to give this a capital T. So it's important that it's a capital T, because we all know when we see capital T that that's a period. And so I'm going to just define that up here. So T is period, and this is the time for one complete revolution or cycle, for one complete revolution or cycle. Okay, so that's usually measured in seconds. It could be minutes. It just needs to be something that has a time to it. So for part A, we want to know the linear speed of the blade tip. So we have this equation. So I'm looking for 2 pi. I know both of those. So R is going to be just my length, right? So I'll go ahead and just define that in here. So this is R equals what I defined as L up here. So I know everything on the top. I don't have the period that was explicitly given to me. So I need to find the period. And the way we're going to find the period is through this over here. So they told us how fast this is going. So the 550 revolutions per minute tells me how many cycles it's making in a given amount of time. I need the inverse of that basically. So I need time per revolution. So there are a number of different ways you can sort of reason through that. I'm going to go ahead and say that we're looking for a time, and I'm going to look for seconds because we want the linear speed in seconds. So I'm looking for the time in seconds for one revolution. So that's my definition of a period. And then I'm going to use what they gave us. So this is 550 revolutions in 1 minute. And then we have 1 minute is 60 seconds. So my units will cancel. And I have, that one went a little crazy. My units cancel. And then I have just seconds left. So I know I've got everything set up correctly. I can quit deleting things here. Minutes. Okay. And we've got seconds. Okay, so we can plug all of that into our calculator and we will get a 0.109 seconds. And that is our T, right? So this is T. So this is telling me to do one cycle, to go once around. Each blade tip is going to take 0.109 second to do that. All right, so I have T. Now I can take that T, and we're just going to plug that into here. So I have all of these pieces. This is, we have 2 times pi, 2 pi, and my R was 3.4 meters over 0.109 seconds. So this is going to equal 196 meters per second. Okay, so this is what we would call, sometimes this is called linear speed. Sometimes this is called that tangential speed. So the speed at that specific point that we're interested in. So this is 196 meters per second. Question B says, what is the radial acceleration of the blade tip? And they want us to express that as a multiple of g. So for B, if we want the radial acceleration, so we just introduce this equation that we can use. So A rad is equal to v squared over r. We just calculated our v squared, so we're just plugging in here. This is 196 meters per second squared, and then over r is 3.4 meters. So that is going to equal, we got 11,300 meters per second squared. So it's a acceleration, so it should have that meters per second squared. And then they wanted us to express that in terms of g. So that means I need to factor out a g. So I'm going to divide that by g. And we end up with 1,150 times g meters per second squared. So that'll be our answer to B. So in this one, so we introduced the idea of the period. So you should recognize that a period is the time to complete one cycle, one revolution, go one way, all the way around a circular path. The speed, this equation here, where the speed is equal to 2 pi r over t, that is not on your equation sheet. So that's something that I'm assuming you should be able to remember, recognize, given the context of a problem. So that's something that we will use kind of throughout the semester as we kind of hop back and forth into circular and angular motion stuff.